Ever tried to build a massive, complex skyscraper without a blueprint? No way, right? You'd never just hand a crew some steel and glass and say, hey, go for it. But honestly, in software engineering, that's kind of exactly what happens when people jump straight into coding. So, in today's explainer, we're diving into the absolute best antidote to that chaos. We're going to talk about transforming complex system designs into clean, easy-to-understand visual blueprints before you ever write a single line of code. Let's get into object-oriented modeling and UML.
Here's our super quick roadmap for today. We'll start with why we actually build models. Then, meet UML, the pictorial language. After that, we'll break down the core building blocks of UML and wrap up with a tour of the essential diagrams you'll need.
All right, part 1, why we build models.
So, what actually is a model? Basically, it's just a representation of something, real or imaginary, from absolutely any domain. But the absolute key here, the really important part, is that a model is way quicker and infinitely easier to build than the real thing. We build them because they give us a fast, completely safe sandbox. You get to simulate, experiment, and wrap your head around a problem without taking on the massive cost and risk of building the final product right out of the gate.
And you know, this isn't just a software thing, it's totally universal. Think about civil engineers. They aren't just guessing a new bridge will hold 1,000 cars, they model the physics first. City planners model traffic flow so they can dodge gridlock before a single drop of concrete is poured. Economists build models of government policy. Heck, even composers write sheet music, which is totally a model, before an orchestra plays a single note. In pretty much every field, modeling is just the accepted, necessary way to build something complex.
So, in our world in software, we really need models for 4 crucial reasons. 1, to visualize the system exactly as it is or as we want it to be. 2, to specify the structure and behavior in super fine detail. 3, to give us a safe template that literally guides us when we're actually constructing the thing. And 4, documentation. We absolutely have to document our decisions so the entire team is always on the exact same page.
Moving on to part 2. Meet UML, the pictorial language.
Okay, let's talk about UML, which stands for Unified Modeling Language. If you're a student just jumping into this, listen up because this is an absolutely crucial distinction. UML is not a programming language like Java, C++, or COBOL. Those are text-based languages that give final, executable instructions to a computer. UML is completely different. It's a standard pictorial language. It relies entirely on visuals to create system blueprints. You don't use UML to run your program, you use it to plan it.
And that really hits the nail on the head regarding why UML exists. Remember those 4 reasons we just talked about? Visualize, specify, construct, document? Well, UML was explicitly designed as the standard way to do exactly those 4 things for software artifacts. It's literally the ultimate tool to map out your software's architecture before you even touch a keyboard.
Also, a quick history note, UML didn't just drop out of the sky. That unified part, it's there for a reason. Back in the day, software engineers were using all sorts of competing ways to draw out their systems. It was kind of chaotic. So UML took the best ideas from 3 pioneers in the field, Booch, Rumbaugh, and Jacobson. People actually call them the 3 amigos. By merging their methodologies, UML became the single, universal standard we all use today.
All right, part 3, the building blocks of UML.
Since UML is a true language, it has its own grammar, right? It relies on graphical elements and very strict rules for how you can combine them. And the whole thing breaks down into a really logical, strict hierarchy of 3 main categories. Think of it exactly like learning to speak a new language. First, you've got things. These are your basic entities. They can be structural, behavioral, whatever. Basically, think of these as the nouns in your sentence. Then you have relationships. These tie those things together and show how they associate with each other. Relationships are your verbs. They describe how your nouns actually interact. And finally, you have diagrams. This is the ultimate output, the complete graph. To finish the analogy, if things are nouns and relationships are verbs, the diagram is the complete, perfectly structured sentence that tells the whole story of your system.
Let's bring it all together in part 4, a tour of the core diagrams.
So here's the thing. One single model is never going to be enough for a complex system. You need different angles, different views. First up is the class diagram. This is where you map out the purely static view of a system. You know, visualizing that a school has a department, which offers a course taught by a lecturer and attended by a student. It lays out the classes, interfaces, and how they relate,
It's kind of like the wooden framing of a house. It shows exactly what the structure is built from, but not really what goes on inside.
But what if you actually want to see what happens inside? That is exactly where use case diagrams come into play. This completely shifts the perspective. Now we're looking at functions entirely from the user's point of view. Say you have an order clerk trying to interact with actions like place order or pay cash. It has nothing to do with the code structure anymore. It's all about what the actual human using the software experiences and needs to get done.
Next, we have sequence diagrams. Now, this one is all about time. It visualizes the exact chronological order in which messages are flying back and forth between objects. You'll usually see these vertical lines, called lifelines, dropping down, and you literally trace time moving downwards. For example, a librarian enters an ID, then checks if the borrower exists, checks for overdue books, and finally confirms the loan. It is literally a play-by-play script of object interactions over time.
Okay, let's do a super quick rapid-fire review to lock this into your notes. Class diagrams, that's your static structure. Use case diagrams, that's the user's point of view. Sequence diagrams, time ordering of messages. And activity diagrams, which are a behavioral category, show the dynamic flow of control from one activity to the next. Combine all these different views, and you get a complete 360-degree understanding of the whole system.
Well, that brings us to the end of this explainer, and I want to leave you with something to really think about. Now that you know models are this incredible, safe, fast way to simulate reality, and that UML gives you this perfect pictorial language of nouns and verbs to draw out a system, ask yourself this. Before you write your very next line of code, what is your blueprint going to look like? Seriously, don't try to build the skyscraper without the blueprint. Take a minute, model, visualize, and document your decisions first. Thanks so much for hanging out and learning with me today, and I'll catch you in the next explainer.